Today we're going to talk about conditional probability. Now, conditional probability means that one event may depend on what happens with another event. And so the example that they give here is that you're applying for a job and you're hearing that 70% have a college degree, get hired. And so when they mention that 85% of the applicants with a college degree and relative work experience get hired, you can then see that the likelihood of getting hired might change based on your qualifications. So we use the phrase given. Probability of an event occurs given that another event has already happened. And so knowing one thing happened affects the probability that something else is going to happen. So we call that conditional probability. So if we're looking at this example that we have here on page 21, same scenario we were just talking about, 200 applicants with a college degree were surveyed. Number of applicants who were hired and who have relevant work experience is in this table here. So if an applicant was picked at random, find the probability of each of the following. So the probability of getting hired. Well, probability of getting hired out of all of it means our denominator is 200. There were 200 total applicants, and those who got hired, that total there is 140. What's the probability of being hired and having relevant work experience? That's again, out of our 200 total, hired and relevant work experience lines up there at 85. This notation down here is what we were just talking about, the conditional probability. This kind of such that sign, that's what means given. And you can kind of think of it as a fraction, such as the part that comes after that symbol is what's going to give you your denominator, and then you use that row to find the numerator or column, depending on what you're looking at. So here it says probability of getting hired given that you have relevant work experience. So if I look at that, I want to know the total who had relevant work experience for the denominator. So relevant work experience total is over here is 100. And out of those who got hired, that was 85. So once you find the correct total, you need to follow that row or column, if it's not the grand total, to find the top part, the numerator, for what you're looking for. Here's the same idea, but in the reverse order. So probability that you have relevant work experience given that you were hired. So again, this second part here is our denominator, and it's always going to be one of those totals from the outside. So the total that were hired were 140, and of those who were hired who had relevant work experience, that was 85. So you can see how these two did have the same numerator. The numerator was those who fit in both categories, hired and relevant work experience, but the denominator changed depending on which one was the given situation. So keep that in mind, order does matter. All right, let's look at kind of the formula for this. So the formula here, and again, this is on your reference sheet, the probability of A given B is the probability that both happened. That's why that numerator was the same, over the probability of the given. That's what this is saying right here. All right, so if a customer from the cafe is selected at random to go with this Venn diagram, what is the probability that the customer ordered a coffee given they ordered a breakfast sandwich? So the fact they ordered a breakfast sandwich, total ordering a breakfast sandwich goes in the denominator. Well, total ordering a breakfast sandwich is this whole circle, so that's 120. And then from that circle, we want to know how many also ordered a coffee. That would have been 80. All right, let's look in terms of percents here. Athletic department was reported that of the senior class, 5.2% are on the football team, 12.4% are the weight training program, and 4.6% are on the football team and in the weight program. Determine the probability of W given F to the nearest tenth of a percent. So I like to kind of write it out so I can see that. All right, so probability of W given F equals the probability, and if I follow this formula up here, is probability of W and F over the probability of the given, probability of F, the second one. So if I go to fill in that information there, probability of weight and football. So that would be this 4.6%. So that's 0.046. And then probability of just the given, so just on the football team, that would be 0.052. So in this case, the 12.4% is irrelevant to what we were doing right here. And so then if you would like to do a basic interpretation of these results, you would write a statement relating your calculated probabilities to student athlete in the given situation. So you would want to kind of divide that out so we could see what that really is. I'm going to do that really quick. 0.046 divided 0.052. That actually ends up being is 0.8846 dot, dot, dot. All right, so the way that you could kind of summarize this is saying there is an 88% chance that, what's this saying? Determine the probability of weight given F. That a student, if you want to call them that, athlete, whatever you want to call that, athlete is in the weight program if they are on the football team, because that's what we knew first. So probability of being in the weight training program given they're on the football team. So once we do those calculations, we get 0.88, which is 88%. All right, looking at a couple more here. Probability that a student at a high school participates in an extracurricular club is 0.7. Probability that a student volunteers in the community given they participate in an extracurricular club is 0.6. Determine the probability that a randomly selected student participates in an extracurricular club and volunteers in the community. So again, we go back to that formula that they gave us. Probability of volunteering given that they're in an extracurricular equals, and then when the formula that we're given says that this one given this one is equal to both of them, V and E, over the given one, which is the second one, E. So then we start plugging in for what we know. They said they participate in an extracurricular club is 0.7, so that's the bottom here. Probability of E, 0.7. Then they say that what we do both is that given is 0.6. So we're given this side this time. And we want to know what is the probability that they do both. That's this right here, the and. So then we need to solve for x. We have a proportion. So we can kind of put this over 1 and cross multiply. So I get x times 1, which is x, equals 0.6 times 0.7, which is 0.42, and that's what we're looking for. So use those probabilities, set them up as equations, those formulas they give you, and then just kind of replace the part you don't know with an x and go from there. All right, I'm not going to do example 8 right now. I want to move on to the next topic. So the other topic we need to talk about today is independent and dependent events. And we can kind of see here what we might mean by that. So this table here is comparing raining to being cloudy, and this one's comparing raining to it being a Tuesday. Now we can probably logically assume that raining and being cloudy have something to do with each other, and raining and being a Tuesday really are not related. So that's what we mean by independent and dependent. If things don't affect each other, it's independent. So whether it rains or not is not affected by whether or not it's a Tuesday. But whether it rains or not is affected by whether or not it's cloudy. So we're going to show mathematically, because we're not just going by opinion here. There is mathematical ways to prove whether things are independent or dependent. So that's what we're going to look at. How do I mathematically determine, are they independent or are they dependent? So first thing we're going to do is we're going to find the probability of rain. That means out of the grand total, they didn't give you any conditions, any givens. So out of the grand total, for both of these tables, it's actually exactly the same. Grand total was 200. Total for rain in each table was 80. Now this one wants the probability of rain given that it's cloudy. So that means the total cloudy is what I need in my denominator. That's 98. And then the days it rained out of that cloudy is what I need in the numerator, which is 72. Then we're going to look at probability of rain given that it's a Tuesday. So total Tuesdays was 30. And from that row, 12 of those Tuesdays, it rained. Now, it's really hard to compare fractions when they don't have common denominators. So it's important to turn them into decimals so that we can compare them better. We're just determining here actually if these are equal or not equal is really all we're looking at. All right, so I just quickly typed those in my calculator, got them as decimals here. So we can see that cloudy and rain, these two here, are dependent. They're dependent since the probability of rain changes based on the cloudiness. That means that these two comparisons here are not equal. 0.4, 0.73, not equal. Tuesday in rain, so then we're talking this one and this one, are independent because the probability of it raining was the same as the probability of raining if you told me it was a Tuesday. You telling me it was a Tuesday didn't affect the probability that it was going to rain. So that's what makes it independent. Those probabilities are the same. The given had no effect on the probability. All right, so that's kind of what that's summarized there down at the bottom. You can read through that if you want. But let's look at some of these mathematical tests where we can determine officially whether things are independent or dependent. So there are two different tests you can use. This is one of them. And let's see if the other one is on here or not. Yes, the other one's on the next page. So this one is that you use a given and see if the given is the same as the overall. And it means, is the probability of the event happening given something else happening the same as just the overall probability of that event happening? And this is just the reverse order, but same idea. So Emily has a pet store. She sells 70% of her products online. There is a 50% chance that a customer will buy a pet toy. If the probability that a customer buys a pet toy, given that they purchase online, is 40%, it can be concluded that these two events are. So let's see. Probability of online is 0.7. Kind of make that a fancy O. There's a 50% chance that we'll buy a pet toy, so probability of toy equals 0.5. And then if the probability that a customer buys a pet toy given they purchase it online, so probability toy given online is 0.4. So we want to know, is this equal to just the probability of given a toy? So these two are the ones we're comparing. So it's the one that's before the given is the one that's all by itself here. So this one is actually irrelevant. I didn't need it. I want to know, are these two equal? Well, 0.5 is not equal to 0.4. If they're not equal, then they're dependent. So yes, buying online is affecting whether or not we're buying a toy. That's what that's saying. All right, let's look at another. Data for the student study habits are shown in the Venn diagram below. Are the events student studies in library and student studies in groups independent of each other? Now, it doesn't matter which order you want to do them in, but whatever order you use, you have to make sure you use the right formula for that. So studies in library, studies in groups. So we'll say probability of library given groups. We'll start with that. And if we're checking for independence, we're checking to see if that's the probability, same as the probability of just the library, just the first one. All right, so probability of library given groups. So that means we're given a group, so we know we're studying in groups, that's 20. And then those who study in the library out of that are 10. And then probability of the library, all right, that's out of the grand total here. So these two together make 25, plus this 10 is 35, plus this 15 is 50. So out of 50, and I'm looking for library. That's this circle here. So 15 out of 10, all right, plus 10, that's 25 total in the library. Well, 10/20ths is 1/2, 25/50ths is 1/2. They are equal, so it wants to know, are they independent? And the answer is yes. These two are equal, so it's independent. Now, we could have done this the other way around. We could have done probability of groups given library, and if we did that, then this would have had to been probability of groups. But overall probability uses the grand total as a denominator. A given uses that given value, which is the second one, as the denominator. All right, one more like this, then I'll show you the other test, and then we're done for today. So here, given the data, are the events of exercising for 3 or more hours per week and following a healthy diet independent? So probability of exercising given diet, we're trying to see, is that equal to the probability of just exercising? So exercising given diet. So let's see, following a healthy diet, we have to add these two together to get that total. So we get 0.5 here. So 0.5 down here. And then those who exercised 3 or more hours a week. So that's the 0.28 here. And we're trying to compare that to this one here. Now we need to add all of those up in order to get our grand total. And we get a grand total of 1 here because these all add up to 100%. So the grand total is 1. And then we want to know probability that they are exercising 3 or more hours a week. So that's our 0.28 plus our 0.12, and that's 0.4. So this is 0.4. If we simplify that, 0.28 divided by 0.5 is 0.56. Now those two are not equal. So are they independent? No, they are dependent. Now justify, we're allowed to use our math to prove it. And here's our math. So we just need to answer the question, which was, are they independent? And we need to have math to prove it. All right, now there's one more formula we can use to do the exact same thing, prove independence. Now I don't love that they're using an X there. I would change that to a dot, but it means times. So this is the probability of both happening is equal to the probability of them each happening separately. That's what this is saying here. So let's look at what that looks like. Based on the survey, determine whether a GPA of 3.0 or higher and participates in sports are independent events. All right, so probability of, probability goes here, of GPA of 3.0 or higher, so we'll say H for higher, and sports. So, and sports. So higher and sports, we want to know, is that equal to probability of 3.0 or higher times the probability of sports? Now, when you do this one, there's no givens. So they're all over the grand total when we're trying to figure this out. So they told us they surveyed 1,200 students. So that's our grand total. And we want to know GPA of 3.0 or higher and sports. So participates in sports, GPA of 3 or higher, that's 452. And then we want to do those separately. Just the probability of 3.0 or higher, that's these two added together. And that is 774. And then we want just the probability of sports. That's these two added together. So that's this. So now I need to multiply these and kind of change them into decimals so I know what I've got going on here. So this one as a decimal is 0.376 repeated. And then I am going to multiply this real quick. 680 over 1,200. And I get 0.3655. So now those numbers are close, but they're not exact. So if they're not exact, then they are dependent. All right, so that's what we're looking at here. So this formula is probability of both equals probability of one times the probability of the other. All right, So let's look down here at, let's look at number 5. Genetics researcher is studying the likelihood of certain traits appearing in a family. Probability that a child in the family has dimples, so I just start writing stuff down sometimes because it helps me to organize, is 0.3. Probability that has a cleft chin is 0.4. Probability that has both, probability of dimples and chin equals 0.12. So we want to know, are they independent, dependent, or mutually exclusive? All right, so, or a combo of both here. So we want to know if the and, 0.12, is equal to each of them separately multiplied here. So 0.3 times 0.4 is indeed 0.12. So these two are equal, so that makes them independent. The other question, though, is are they mutually exclusive? Is one happening without the other one happening? Do they have to, can they, I don't know how else to say it, but like both of them can happen at the same time. So if both of them can happen at the same time, then they're not mutually exclusive. So it's just independent in this case. All right, they both can happen at the same time. So they're not mutually exclusive. All right, last one. Streaming service analyzes data to understand its subscribers' viewing habits. After its analysis, it discovers that the events S, that a subscriber watches sci-fi movies, and D, that a subscriber watches documentaries, are independent. The following data are given in a report. Given this information, we want to know what the given is. Well, these things are not all in the same formula. So if I were to use this one to check for independence, I would need this, and I would need the probability of S. Well, I don't have that. If I wanted this for independence, I would need to use this, the probability of D, and then the probability of S. Well, I know the formula, so I can use the fact that I know they're independent to find the probability of S. Then I can use that to find the probability of the given. So if I use this piece here, and I set this up in the formula they gave me, they told me the probability of S and D is equal to probability of S times the probability of D. Because they told me it's independent, that means I want to use that formula. So this was 0.24, this was 0.6, this we don't know, so let's call it X. Well, to get X on a side by itself, I divide by my 0.6, and 0.24 divided by 0.6 gives me 0.4. So 0.4 equals my X, which was probability of S. Well, now I can use my other independence formula, which says probability of S given D is equal to the probability of S if I'm independent. Well, this is 0.4. We know we're independent, so this had to have been 0.4 as well. And there we are. All right, go ahead to Delta and try out the problems that I left for you. Please let me know if you need anything. You can come into AA and we will recap in class the next time that I see you.